So this is, I think, 2/3 mark. I think we have finished 2/3 of the semester, I suppose, if you go by the number of weeks. I think that's how I got this count. And yeah, that means we have 4 more weeks before Thanksgiving and 1 week afterwards. That's what it was, and excluding the exam. So, so just to, we had a homework due today, and the next homework, so this will be homework 11 and a homework 12. So notice that this is to your midterm 3 next Friday, not the coming Friday, 1 week from Friday. So that's November 6th, right? That's 1 week from Friday. So I want to make the homework due before that. So I'll make the homework 12 due November 4th. It should be a Wednesday. And then there is not much room there, right? So I was thinking I'll make a very small homework and make it due October 30th, or I can make a single homework that's due on all the way on Wednesday. What do you guys, any suggestions as such?
Well, maybe, I guess for me personally, one homework would be easier
homework.
to
Okay. Yeah. Let's make that. So. So it might involve both the topics. It's not both actually. There is one small topic which you get used to go into the next topic. Okay, so note that down. Okay. So we talked about method of images, which is basically to find out the electric potential around conductors. So we would like to do this from a little more fundamental way. It was more of a methodology, right? We realized that, oh, this does the job. So let's look into this a little more closely. We would like to write differential equations for in the presence of conductors. That's what we want to do. But one step towards that is what we call boundary conditions. So it's called boundary conditions. At interfaces or at an interface. Let's say. What we mostly want to do is it's pretty much like optics. So let's say there is an electric field. So there's a surface. This is epsilon1 on one side, epsilon2 on the other side. These are the two dielectric materials we have. Right? Is that readable? Oh, maybe there's a reflection.
Yeah.
Yeah. Not much you can do about that. Okay. Yeah, so there is a region where on one side of an interface there is a dielectric material epsilon1. This could be air, for example. And on the other side, there is another dielectric material. It could be glass, right? That's what happens in optics. Something, imagine that. And think of electric field. Usually we talk about the ray of light. We won't talk about electric field. Like that's your electric field. So it's not uniform in any sense. That's a electric field. This could be, there could be a charge here. It seems like it is originating from there. That suggests that that might be a charge there. And we would like to know, how does this electric field go on that side? Right? How do you extend? Is there a rule? Like if it was a ray diagram, then we would say, oh, Snell's law also. Is that how we go? So recall, right? Recall Snell's law. Oh, that's extra cryptic. State Snell's law for optics. Snell's law, and which basically tells us that if you have an interface, what do we do there is refractive index N1, refractive index N2. Yeah, so extra credit, I'm going to tell something about Snell's law. So for you guys, pick it Snell's law and Fermat's theorem. You can derive Snell's law from Fermat's theorem. So, right, find out what Snell's law, what's the connection between Snell's law and Fermat's theorem. So if we have two, in optics you call it two mediums instead of dielectric material. You say there is a refractive index N1, there is a refractive index N2, and we don't talk about electric field, even though it will look very much the same. If there is a ray of light, so this is a ray of light, this is electric field lines. And what Snell's law tells us is, if N2 is greater than N1, that means it's a denser medium compared to N1. In that case, if you have a normal line here, instead of this ray of light going straight, this will bend in such a way that this angle θ1 is a little larger than the angle θ2 it makes with the normal after getting into the medium. And there is a law that governs this, that's called the Snell's law. And this happens in such a way that N1 sine θ1 is equal to N2 sine θ2. In fact, you can derive this using Fermat's theorem. So that's also a nice way of calculating that equation. In fact, when you do optics, it's almost given as a law, but Fermat's theorem lets you derive that. So it's a maxima minima principle, and it's a very nice derivation. I will encourage you guys to attempt on that. So that's correct. And also remember that I have suggested that N1 actually is square root of epsilon1. So refractive index is square root of epsilon. Technically, it is real part of epsilon, but if we are doing static situation, there is no frequency dependence, and then it is just square root of epsilon. But now we are asking, what about electric field? Does this satisfy something like this? Does this bend this way? Does it go, instead of going straight, this will go this way, or bend the other way? We would like to investigate that. So let's go back to our equations. We want to do that from very scratch. So this is electrostatic, right? Let's stick to electrostatics. A very similar derivation is possible for magnetostatics also, or in general for electricity and magnetism, and even in the dynamic case. But let's do this for electrostatics today. So electrostatics, in the way we have constructed our equations now, is the divergence of the constitutive field is equal to rho of R, the charge density, and we have the cross electric field is equal to 0. But what's the connection between the displacement vector and the electric field? That's looking like this as this is in general a tensor. Notice that each one has its own time dependence. Just for your information, if there was a time dependence, this is defined in the Fourier transform. The more generic, if you were to involve time dependence, you don't do this as time, you define this relation in the frequency space. And in that case, this is a true statement. Where each of this is, each one of this are Fourier transforms of the respective quantities, respective fields. Like D is the Fourier transform of D of RT, E is the Fourier transform of RT. So this definition by construction or by definition is in the Fourier world, or you can say in the frequency space, and that's because most of the measurements are actually done in the Fourier space. So what about statics in Fourier space? What does statics mean? So statics in Fourier space is implies that omega is equal to 0. Right? Remember that frequency and time are sort of inverse of each other, even if you think of it in very simple time period situation. So that's 2 pi over time period. Right? So if for statics time period is infinity, so omega is equal to 0. So that's a simple way of looking at it. But even more concretely, one can show that it is omega equals 0. So when I write this down, it is it means that this is d of R0, epsilon of R0, and e of R0. Okay, so that's your electrostatics equation. And now we would like to analyze this for a situation of this kind. And we'll come back to the planar case. Planar case is much simpler, so that's what we will work with mostly in the next few classes or weeks actually. But before that, let's do this more generally. Like, what if you have an arbitrary conducting surface or arbitrary interface at this point, right? So we would like to know. So this is an interface, an arbitrary interface, and there is epsilon 1 here, epsilon 2 there. So this is an interface. And we would like to know how does the electric field move, or what are the conditions that needs to be satisfied right at that boundary. Okay, so let's start with the first equation, right? So what we will do is let's draw that fresh and keep referring to that. Okay, so let's have a surface epsilon 1, epsilon 2. And I have this to be a volume. Notice that this, so if this is an interface, this is coming out of the board, and this volume is to be thought of as a cylinder. Cylinder, the same thing. Is that clear? Right? That's a volume which is constituting of a cylinder and two faces associated with it. The faces of the cylinder are chosen to be parallel to the interface. So this is typically called cylindrical, or just a pillbox, I think. Typically, I think maybe in the olden days the pillbox was of cylindrical shape, like with phases parallel to the interface. And side in the single side of infinitely small height, let's say delta. So that's delta. Okay. So we would like to take this very tiny, really squeezes the interface in between that. And since that's a volume, I will integrate my first Maxwell's equation that causes d capital. Let's see. D and that's equal to 0. Sorry, that's equal to dqr times rho of r. Right. This is the volume V. Integrate over volume V. So let there be no charges on the interface. Like it's unlikely that there will be a charge on the interface. We are going to take the extreme scenario where this is actually a conductor, so we don't expect to keep it there. And even if it is really close to the interface, we can, since this delta is infinitely thin, we can actually go further and further down. How much ever close it is, to make the delta smaller than that. One might wonder, what about induced charges? We said the conductors pull charges from ground if this is connected to something, but that is contained in D. Right? Of course, there is induced charges, but all the induced charges are in D. So induced charges are inside D. Induced charges are in D. Which means that this is actually 0. I can choose my delta to be as small as I want. There is no charge in there, so that's equal to 0. So I have Q R divergence of D is equal to 0. That's clear. But if using divergence theorem, this is nothing but the surface integral of the whole pillbox is equal to 0. This pillbox has 3 surfaces, right? Two faces and one side, which is pretty much a circular side. And let's have this to be your N1, so that's 1, and that's your N2. The unit vectors, right? N1 and N2, which is perpendicular to the interface. Okay. So I can write this. So remember, two phases, three phases in total, two phases and one side, right? One side phase, if you want to call it. So this is dA, and there are two phases. It is N1 dotted with D1, D evaluated on the left, on the side containing the 1. So let's say this is 1. So this 1 means that this is evaluated slightly on the E1 side of the interface, and I have the other quantity, which is D2. The 2 here, 2 subscript, means that I'm evaluating this electric field or the displacement vector on the respective side of the interface. But that's only 2 sides. The third one is, that's also an area. That's also an area. But now it's what do you call it? It's the vector that is perpendicular to the face is actually S, if you want. Let's call that S, or better, let's not call it S, let's call it N perp. So notice what is the notation here. If you have a surface that is a normal, that will be considered parallel. So this is parallel. Parallel to what? Parallel to the normal vector. And this quantity, there are 2 directions to this. That's considered the perpendicular. There will be a lot of literature which says parallel with respect to the plate. The interface is used to be the parallel, but notice like interface is a surface, so it is not a very unique way of doing that. So we will always try to have a parallel to the normal vector. So in this case, so this is N perp dotted with D. And this has to be done over this whole face, right? It's a circular face, but then this also has a limit, correct? This is plus limit delta tends to 0. As I take the limit delta tends to 0, this thickness of this area goes to 0, and in general, this will be equal to 0. This whole thing will be equal to 0 because we have an area that's going to 0 area multiplied by the displacement vector, unless the electric field of the displacement vector goes to infinity. Remember, this is D is epsilon times electric field. If electric field goes to infinity at the interface, then this has a chance to survive. But we are saying everything is normal. The dielectric function is not infinite, and the electric field is not infinite. If that's true, this implies that the normal vector N1 dotted with D1 is equal to minus of N2 with D2. Instead of writing N1 and N2, use one of them as the normal vector and choose the other to be perpendicular to the other surface. So I can write this as now to change the notation, N hat dot with D1 is equal to N hat dotted with D2. So here N hat is equal to, let's say, N1, and N hat is equal to N2 on the other side, on E2 side. So it is, so when I say no subscript, that means it, where you are decides your normal vector. If you are in the second side of the interface, then N is in this direction, and if you're on that side, N1 is on that side. So accordingly you choose that. So by not writing the interface, I've said that D1 decides that. Any electric field can be broken into parallel and perpendicular. So it is good to write. So this is N hat. So before that, so there's this electric field. It is easier to just consider parallel. So let's say so D is write that as N hat dotted with epsilon 1 on the left hand side, right? When I say epsilon 1 on the left hand side times electric field. E1 is equal N1 N hat dotted with epsilon 2 times E2. The dielectric function can come out. So this is epsilon 1 times N hat dotted with E1. That's the parallel component of the electric field. So what we have learned is that just because we have Gauss's law, at the interface, the product of epsilon 1 and epsilon 2 has to be the same. And what is parallel here, it is good to clarify. So if you have an interface here, let's say at some point here, right at the interface, there is an electric field. That's your electric field at that point. So that could be on 2. So this is 1, that's 2. So that's E2 vector. What do I mean by parallel here is that first take the normal component, that's this. The component of the electric field normal to the vector is E parallel. So this is E2 parallel. And this length here is E2 perpendicular. And of course, E2 doesn't have to be in the plane, right? It could be coming out of the board. If I choose my plane to be coming perpendicular to the board, then electric field could be in a direction coming out of the board, and E2 parallel is in that direction. It's also coming coming out of the board, but this is always in the board. This is in the direction of it. So that's E2 parallel, that's E2 perpendicular. And this will be angle theta, right? If we can describe our angle theta as tangent theta. If you want to connect with Snell's law, it will be E2 tangent theta 2 will be E2 perpendicular over 2 parallel. Right? That's what your conditions are. But what we have learned, we have not reached there yet. What we do know is that this is true. So what will happen in this case? What we have, so let's say this is again an example, right? We have epsilon 1, and let's say epsilon 2 is greater than epsilon 1. And let us say the electric field here, right at the interface on the first side is this. So that's your electric field. And that's your E1 parallel, and that's E1 parallel. How will the electric field be on the other side? Now, one thing we can be sure of is that if epsilon 2 is larger, the E1 parallel has to be smaller, right? These two have to be the same. If epsilon 2 is larger than epsilon 1, electric field on the second side has to be smaller than epsilon 1. So that much we can be sure. So what we can do is that whatever electric field we draw here, right? We don't know how far, how much is the length, but this one we do know that this is smaller than this. That's your E2. That's for sure. So if E1 parallel remains the same, that means that it will be bent like this. So let's see what happens to that. So let's again do a calculation to see what about parallel or the perpendicular component. Right now we know something about the parallel component. What about perpendicular? So, but we have one more equation, correct? So we have the curl of the electric field also. So let's take the same similar surface. We have epsilon 1, epsilon 2, and this time we don't take a volume, we actually consider a surface. This is a rectangular surface. Surface perpendicular to the does it mean perpendicular to the interface, right? That's perpendicular to the interface, and one side of length delta. So it's like it's not one side of the length delta, it will be 2 times delta, but it has a measure of delta. So in the limit delta tends to 0, this becomes an infinite within strip. And it has to have a sense now of going around. So let's say that if we go around that, this is this. We want to use Stokes' theorem, and we want to go around that. So let's integrate on the surface. This is the surface we are integrating on, dotted with del crossed with electric field is equal to 0. Because the cross of the electric field is 0, integration over that also has to be 0, and this is equal to 0 everywhere, right? If we are in statics, that's perfectly fine. Again, break this into 2. So we have dl times before that, I should use Stokes' theorem, right? So Stokes' theorem says that this is EL dotted with electric field is equal to 0. Go around the loop, and there are 4 pieces to that. So this is the 2 of them are parallel to the interface, and that one I pick as S1, or yeah, it's perpendicular, right? And third on the second side, let's say this is third on the second side, dotted with electric field, plus N2 curve or N1, N1 curve dotted with E1, plus DL, but that has a limit delta tends to 0. These lengths actually have to go to 0. And that one is perpendicular to that. So it's N half dotted with E. But whatever that is, this is equal to 0 in the limit delta tends to 0, because you can squeeze that as much as you want. And if the electric field does not blow up there, that means it does not go to infinity at that small region, then we can be safe that this is equal to 0. And so we are considering those scenarios. This implies that Q or let's say, and 1 is equal to N2 or dotted with electric field. And this tells us, again, make it N perp actually, irrespective of which side your understanding is that perp actually selects that one out. And this is nothing but the perpendicular component. Remember, perpendicular component means the component that is, in a sense, parallel to the surface. So perpendicular to the normal vector. So we will call this E1 perpendicular is equal to E2 perpendicular. No dielectric functions showing up. Right, so these two are exactly the same. So if we go back and analyze this, so this length remains the same here. Right? So this length remains the same here. So it should be like this. So that's E2 perp. That is exactly the same as this. This one got shortened because epsilon 2 was larger. And now if you notice, I cannot go straight, right? If I were to go straight, I will hit here, right? Because that's slightly smaller, so it is actually bending. So electric field lines actually deviate away from the normal in this sense. But what happens typically is that one should be careful that this is the ray of light, right? So this is a ray of light. That has to do with the direction of propagation, right? Propagation is the direction of propagation. And electric field lines are perpendicular to that. Remember your electric field lines diagram. That's your field lines, correct? These are vectors actually. They oscillate. We are of course not talking about electromagnetic waves because we are not talking about dynamics here. But typically, if you want to connect with the Snell's law, then electric field is always perpendicular to the direction of propagation. In fact, there is a magnetic field also. Magnetic field is coming out of the pole, right? In this case, so this is perpendicular to that, and all three are perpendicular. And that's your motion. So this diagram, rather than drawing it like this, it's much better drawn if you were to think of with respect to the ray of light. So that's your ray of light. That's ray. Right? And electric field is perpendicular to that. Electric field is perpendicular to that means that this is electric field right when it touches here. And now we can again say what is your parallel and perpendicular. That's your perp. Let's say epsilon 1, epsilon 2. That's your E1 perp. That remains the same on the other side, but this is going to get shortened. That's your E1 parallel. The moment you go inside, this has to get shortened. This stays the same, this has to get shortened. So it gets shortened here. That's your shortened vector. If that gets shortened, this is my vector now. That's the vector E2. And my ray has to get perpendicular to that. So accordingly, so this was your perpendicular here. Now the light has bent now because this has to stay perpendicular. That's your angle theta, the deviation, if you want. So that's the deviation angle. So if this is theta 1, that's your theta 2. Is that clear?
So the E1 equals E2 is the answer for the perpendicular
Yes, so whenever there is an interface, the perpendicular component remains the same. This is the message you want to take home, that the perpendicular component has to remain the same. That's a boundary condition. And the parallel components, they adjust in such a way that the interface is taken care of. Like if this is larger, this will be smaller. If this was smaller, that's larger. Right? If this one is larger than this one, like if this was larger than this one, then this one will be smaller, because the product has to remain the same. Is that clear? And that's what I'm analyzing here, that the electric field comes in here. That's a ray of light. Electric field comes in. It was of this length. The moment it gets inside, this length shortens, correct? Because this is greater than 1. So that shortens, and that's your new electric field. Once that is a new electric field, then my ray of light switches accordingly, because the ray of light is to be perpendicular to the electric field. Is that clear? Right. And this is angle theta 1. That will be angle theta 1, right? This is angle theta 1, 90 minus theta 1. So that's angle theta 1. If you want to enlarge that figure there, you can actually say something about the directions. So at that interface there, that's the box. Doesn't have to be a square, so that's it. Right. That's your electric field E1. That's the electric field E1. This is this line here, E1 parallel. Right? That's the normal to that. And this is E1 top. Right at the interface, this switches. This is right before it, right into it. It switches. How does it change? This remains the same, so that the third component has the same length, but this one gets smaller. So this one gets smaller. If I'm saying that 2 is greater than 1, that means this will be smaller. That's the 2 parallel. So if that's the case, so that's your E2, that's your new vector E2. The ray of light itself was at this interface. This was perpendicular to that. That was your ray of light. That's the ray of light here. And it was making an angle theta 1 here. If this was theta 1, then this is 90 minus theta 1. That's your theta 1. And what is tangent theta 1? It's better, right? What is actually staying the same, maybe what shall I say? E1 parallel. What was I trying? No, yeah. So let's do tangent theta 1, right? So tangent theta 1 is equal to E1. Tangent theta 1 is E1 parallel over E1 perpendicular. You can do the same thing for tangent theta 2. It will bend a little here. This goes this. That's your theta 2, right? But that's 90 minus theta 2, so that's theta 2. And tangent theta 2 would be equal to, again, same idea. So that's E2 parallel over E2 perpendicular. So we do know that using the second boundary condition that E1 perp is equal to E2 perp. So we get a relation here. So E1 perp is equal to E2 perp. That means that E1 parallel over tangent theta 1 is equal to E2 parallel over tangent theta 2. And that's your Snell's law in if you want for electric field. That's your, if you want it in terms of angle, but it's not very useful because these are the materials, and this is the best. This one and the second relation, right? E2, whatever Gordon you were asking. Okay, open. But you'll often see this relation being written out. These are the boundary conditions in terms of material properties, but these are the boundary condition in terms of geometric properties of the electric field intersecting at the surface. And I'll stop this, and just to give you a hint of what we are doing now. What happens? So investigate what will happen to the epsilon if you are in a conductor. Inside a conductor, on the left side of the conductor, that's air. So this is you don't have any choice. On the right side, electric field has to be 0. So the only way this can be finite and you get right side not to be 0 is that this is infinity. So a perfect conductor, which requires electric field to be 0, requires this to be infinity. So the dielectric function for a perfect conductor will be 0. And that's what we will use and proceed and write down differential equation, because when we write differential equations, we want boundary conditions, and that will be our boundary condition, that on the surface of a conductor, the dielectric function is 0. Already we know that the electric field has to be 0. What about electric potential? What is the electric potential inside a conductor? Constant. It is not 0. It's not, we don't know what it is. It depends on what voltage you provide. If you ground it, it is 0. So it is constant, electric field is 0, and now we also know that the dielectric function has to be infinite. So let's stop there. Okay.